All right. See what I can trip over now. All right, so this is Newton's Law lab. Newton's second law lab. So what we want to show is that the total force is equal to mass times acceleration. And so typically written this way, or as Newton, closer to what Newton did, acceleration is force divided by mass. And sometimes I will write this as force like that, indicating we're adding it up. This is a math symbol here representing a sum. So I'm adding up all the forces, that should be mass times acceleration. Or sometimes write F net is mass times acceleration. So in this particular lab, I've got a 20-gram mass right here. I have, on top of the cart, I have two 20-gram masses and two 10-gram masses. So I want to predict, first off, what the acceleration is, and then we'll discuss about why it's not right. I guess I should wait for it not to be right before we continue, because maybe we'll nail it. So, what is the net force that is going to be pulling on the cart?
20, whatever you said, kilograms?
Those are grams. Those are in grams right there. So the current setup, table, track, cart. And I have 20 grams here. And then on top of this, I've got 10 gram, 10 gram, 20 gram, 20 gram.
So pulling on the cart would be the 20 grams, right?
I'm gonna nitpick.
No, because it would be 20 times 9.8.
Closer, yes. Well, it depends on what unit you want in the end. But yeah, it's the weight of this which is pulling on it. Now from a force diagram point of view, I've got cart here with wheels. It's being pulled on by the rope. And then I've got the rope here. The rope is being pulled back by the cart. I've got my 20-gram mass down here, so it has its weight. And then I have the rope holding it up and the rope being pulled down. And there's also a normal force here acting on the rope. Now, if we're considering the rope to be massless compared to everything else, we can ignore these forces right here acting on the rope itself. Y sub R. There's a weight here and a normal force there, cart. And weight of H for hanging. It's the hanging weight. Now, if we want SI units, we want the international standard units, we wouldn't do 20 grams times 9.8 meters per second squared. What would we do?
Kilograms.
So how do you get from grams to kilograms?
Use the decimal place
1,000.
over 3 places.
Yep, 3 places are, you'll end up dividing by 1,000. And so my mass here, 0.020 kilograms. And so the weight, 0.020 times 9.8, which is 0.196 kilograms.
Yeah, that's right.
Okay. All right, so we have 0.196 kilograms. What's the total mass?
The mass is 0.02 kilograms. That's the mass.
Let's see if that makes any sense. Times my acceleration. And so my acceleration becomes 0.196 over 0.02, which is 9.8. So what you're claiming is that if I let this thing go, that thing is going to basically accelerate like it's in free fall.
No.
So what is the total mass?
0.06 kilograms.
Say it again.
Said 0.06.
How'd you get that?
Of the cart.
Let's try it out. We got a prediction now. 196 is 0.06 times A. What should the acceleration be then?
.267. I don't know, there's a bunch of sixes.
Okay, that's fine. Units?
Meters per second squared.
All right, so let's find out if that's true. Now, in order to find the acceleration, we got a couple different ways that we can do this. One of which is we could do timing. We could put set a photo gate up, make sure that this trips the photo gate almost as soon as you let go of it, time how long it takes to travel a set distance, and then plug into the formula Hewitt's version, d is equal to 1/2, or you know what? Not Hewitt's version. The displacement is 1/2 times the acceleration times time squared, because we're going to start it at rest. So that's one way of doing it, and that's the way that this lab was conducted several times in the past, until I came up with what I hoped was a simpler method. If the acceleration is constant, then my position versus time graph, that's what I want. I think I just need a camera operator in order to follow me, but, or what is the thing which follows you as you go? There's some device that you hook up to the camera. Okay. So if acceleration is constant, the position versus time graph is part of a parabola. Parabolas basically look like that. If I throw an object in the air and if you actually track the motion of it, it's basically going to look something like that. Because once it leaves my hand, the acceleration is constant because the only force acting on it is its weight, which is downward. If it's part of a parabola, you're going to end up with the position is equal to something times t squared plus something times t plus something. This is just a generic equation. In math class, they would label this as probably A, B, and C, something clever like that. It turns out that this number right in front of the squared term, this is 1/2 the acceleration. The thing right in front of the time squared is 1/2 the acceleration. So if we use the motion sensor, we should, and track that thing, we should see part of a parabola. All we have to do is go into that, zoom in on it, and see what the equation is, and just see what's in front of the squared term. And that's half the acceleration. That is simpler because you don't have to worry about timing it, because before, when we had the two photo gates, if it was back too far when you let go, you had some initial velocity when it hit the first photo gate, thereby making this equation invalid because this assumes it starts at rest. Let's see if we can work this out. So I have a motion sensor, I have a lap quest over there. Digital port, and I hear the familiar clicking. I want to increase the sample rate, so I clicked on samples, and I'm going to change the rate to 50, because that's the maximum that we can do. And I want the bit duration, I'm going to make it 10 seconds, just to give me a little bit of leeway here. Oh, I've done this so incredibly awkwardly. You know what, it's going like that. So this is similar to what you did in the linear motion lab, except for the fact that we'll have something else driving it as opposed to you just putting your hand up and down over it. Now, while it is moving, it should be a parabolic curve. As soon as this mass hits the ground, we have an additional force involved. As soon as the hanging mass hits the ground, the tension drops off to almost zero, and this thing is just going to coast. What you would probably see is it's going to look like a parabola, and then it's going to curve off. So when we do the curve fit, when we try to figure out what is the part while it's actually accelerating because of that hanging mass, we need to do it before it starts to curve back. So we'll probably just highlight an area like this. And let's see how it goes. Also, anything within 17 centimeters is not going to be acknowledged, so why don't we back that up. I also want the screen to be as perpendicular to the track as possible. So I'm going to have to trust, I guess Stephanie, you might have the best viewpoint, or somewhere along the line, how do I need to?
No, it's good.
Good enough? Yep. Stop swinging. Let's not get. So that's about 17 centimeters away. It's over there. Would someone be kind enough to?
It's not on, it fell off the track.
It fell off? Oh, it fell off the pulley. All right. So, whenever you're ready, just start it, and then as soon as it crashes at the end, stop it. It fell off the end, sorry. That's it. You mean this frayed string is probably not good enough?
Do I have to clear anything, or can I just stop it again?
That first trial was garbage.
I think you needed to start another trial.
As soon as you when you hit go, it should ask you if you want, it's either gonna start a new run or it's gonna ask you, do you want to delete it?
No,
Just hit that little thing next to red one, yeah.
All right. If this also fails, then what I'm gonna do is get a different string, so there'll be a small intermission, whenever you're ready. All right.
Would you like me to turn the camera so you can see the
Oh,
position?
yeah. That'd be good. Battery power, I have almost no battery power here. All right, let's do this. So we have our two runs right there. Well, you know what? You're going to watch it sideways. All right, so you notice that top one right here that is the position graph. So you got that really nice looking curve there.
Someone turn off the front light because you can't really see the graphs very well.
There's
Oh.
a slight glare.
Yes. If someone would be kind enough to get the light.
Okay. That's better.
How's that?
That's a lot better.
All right. So we get this nice parabola here. And this is the point when I personally stopped it. But sometime before then, the mass had hit the ground, the 20 gram mass had hit the ground. So I'm going to just come in some and pick part of the. That seems reasonable. It already has started moving down here because it looks flatlined, and then suddenly it picks up. Notice the velocity is steadily increasing. And if we look at the acceleration, I'd like to think the acceleration is going to be constant, but probably hitting grid or something like that in the track in that spot right there, which corresponds to a little bit extra bumps right there. But let's take a look at acceleration just for the fun of it. And that is really misleading. It looks flat, but the thing goes, those are really messing up. So let's do graph. Zoom in here. And so you have an acceleration that's relatively constant, except for this little blip right here, and then goes relatively constant again.
So does it stay constant?
It'll stay constant as long as the force is constant. So as long as that mass was still falling, it should have been relatively constant. All right, so analyze, curve fit. I want to curve fit the position. I want to do a quadratic fit. And I look at this acceleration right there. Oh, sorry, that is the coefficient, that A is the coefficient of the square term, so that's half the acceleration, so just double that number. And you get an acceleration of just shy of 0.32 meters per second squared. Can you see it?
No, I don't understand what you're. Oh, we're looking at A. So the number you want us looking at is 0.
That's 15988. And the acceleration would be twice that number. So we have an experimental acceleration of 0.31 something,
976.
0.31976 meters per second squared. And our prediction was over 3 meters per second squared. So, why are we off that much?
What did we think it was going to be?
3 point something. So,
Okay.
let's see if I mute this blank. That was our prediction. And that's what we got.
Where did the 0.6 come from? 0.06?
Is there a problem?
No.
I don't think we were able to calculate in the mass of the car itself. Just had the masses that were on top.
So what should we include?
The mass of the car?
Yep. Think about all the things that are moving. All the things that are being accelerated here. We have the mass on top. We have the cart itself. And what else do we have?
The hanging weight.
Yes. The hanging mass is also part of it. So we have the hanging mass, what's on the cart, and the cart itself. Since this is a crude demonstration, if this were the actual lab, we'd go through and we'd find the mass of the cart. But the mass of the cart is it's roughly a half kilogram. So 0.5 is kilograms is the cart. On top of the cart was 0.06 kilograms, and then the hanging mass was 0.02 kilograms. So we end up with 0.58 kilograms approximately. So now our prediction therefore would be, we still have the same force trying to drive it all, the 0.196 newtons, and that's equal to 0.58 times the acceleration. So the acceleration is 0.196 divided by 0.58.
0.3379.
3379. And now we're a whole lot closer. So we're about 5% off. See how well this holds true. Certainly,
Do you want me to just hold it?
not quite. Yeah, let's see if I can. Okay. So now I'm going to take one of the masses off the cart and I'm going to put it down here. Now these things are designed, if you push this up a little bit, there's a hook on the bottom. It's designed so that you can string them together, in theory, like that, so you can get a whole chain of them. The disadvantage of doing this is that this is going to hit the ground sooner than the other one did, and so I tend to, hook them like that or hook it around like this, so that it's not hitting the ground any sooner and causing us to lose data. All right, so now I've got 40 grams hanging on the end there.